My last example inspired from population ecology is that of prey-predator dynamics. So in this example, we imagine we have an ecosystem that contains rabbits and foxes. And the rabbits left by themselves multiply like rabbits, whereas rabbits are eaten by foxes. So the equation of motion for the density of rabbits, and now let me use R so I remind myself in talking about rabbits, is R dot is equal to 3R, so they reproduce very productively. But then they're eaten by foxes, minus 2RF. Whereas the foxes, if they're left by themselves, they don't eat the grass that's around, and so they just starve to death. So they just die exponentially. But when they eat rabbits, they can increase their population. So this model is completely unrealistic, but because it's simple, it turns out to be a useful paradigm for understanding various types of oscillatory dynamics in competing ecological systems. Let's analyze the behavior of this system of equations. So the first thing we might want to compute is this linearized transformation matrix, and then evaluate it near the fixed points to look at the stability of the different fixed points. So the linearized transformation matrix is just 3 minus 2f minus 2r, 2f, and minus 1 plus 2r. Now what are the fixed points of the system? Well, 1 is obviously 0, 0, an empty ecosystem. And in that case, the transformation matrix would be equal to 3, 0, 0, minus 1. And the eigenvalues are equal to minus 1 and 3. So that means that this is a saddle point in the state space. So if I look at rabbits and foxes on this axis, then this point is a saddle. And if there's only rabbits, they multiply exponentially. And if there's only foxes, they die exponentially at the end of the system. The other fixed point is the non-trivial fixed point, and it turns out, and it's easy to figure out for yourself, that it's at 1/2, 3/2, coexistence of the two species. And at this point, A is equal to 0 minus 1, 3, 0. And the eigenvalues of this, lambda plus minus, are equal to plus or minus I root 3. This is a center. So that means that in the state space, rabbits, foxes, there is a point here where orbits go around. Now, that means that if I look at as a function of time, both rabbits and foxes are oscillating as a function of time. And in fact, data from catches of lynx and hares in the Canadian Arctic from many years ago shows this oscillatory behavior. However, this oscillatory behavior is not anything realistic, because it turns out that each of these orbits, closed orbits about the center, the fixed point, are marginally stable. That is, that there's no flow inward or no flow outward. And if I perturb the system and move to another orbit with a larger amplitude, it stays there forever. So these are called marginally stable orbits, and it's not a terribly realistic feature. But the one thing I wanted to emphasize here is that there's buried inside of this dynamics is a conservation law, and it's a simple strategy when you're dealing with quadratic equations to do some manipulations to try and ferret out such conservation laws. So let me just mention the existence of a conservation law in the system. And so this is a general strategy that you can adopt whenever you're dealing with quadratic equations of motion. Instead of looking at the equation of motion for r, let's look at the equation of motion for r dot divided by r. Because on the right-hand side, we change it to a linear equation. It's just 3 minus 2f. But r dot over r is the same as the derivative with respect to time of log r. Similarly, let's look at the equation of motion for f dot over f. And so that's equal to minus 1 plus 2r. And that, in turn, is the same as log f, the time derivative of that. Now let's take this second equation, multiply it by 3, and add these two equations up. And let's see what we get. So on the left-hand side, we have log r dot plus 3 log f dot. And on the right-hand side, the 3 and the 3 times minus 1, they cancel. And so I'm going to have 6r minus 2f. Notice what the right-hand side is equal to. It's the same as taking my original equations of motion, adding them up, and multiplying by 2. This is the same as twice r dot plus f dot. So amazingly, there is a conservation law that log r plus 3 log f minus 2r minus 2f is conserved. And it's the presence of this conserved quantity, an energy-like quantity, that is why we have closed orbits, because when I go around in an orbit, if there's a conserved quantity, when I come back to the same point, because there's this conserved quantity, I do have to come back to the same point. This is a cute feature of this prey-predator dynamics. Again, I want to emphasize it's not terribly realistic in a real ecosystem, but it's a nice piece of mathematics that goes with this prey-predator dynamics.